Most creek hunters pass right over it, a scuffed, angular gray pebble, dull to the eye, oddly heavy in the hand. It doesn't glitter like quartz or flash like mica, yet this unremarkable companion often travels with something far rarer: raw diamonds. The earliest clues are usually not diamonds themselves, but the company they keep, indicator minerals and sediment traps that signal a diamond's long, silent journey from deep earth to shallow stream. Diamonds in creeks are almost never found lying loose on the surface. They move differently than lighter gravels. With a density of about 3.5 g/cm3, raw diamonds are heavy enough to settle quickly, even in fast flow, yet light enough to be displaced again by seasonal floods or seismic shifts. This puts them in a unique behavioral category: mobile but selective. The stones end up in traps, depressions in bedrock, downstream of boulders, at the inside curve of meanders where flow velocity drops. These are the same places gold hides, but the diamond's density means it often stops just short of where heavier black sands accumulate. One of the biggest missed opportunities is the failure to read these sediment signatures. When a creek exposes a bedrock lip or false floor, a compacted clay layer, for instance, most casual collectors focus on the shiny stuff above. But beneath that upper veneer, heavier materials concentrate in microlenses. It's in these fine zones, invisible to the casual glance, where raw diamonds and their companions can rest undisturbed for centuries. The surface clues aren't flashy. No crystal sparkle, no vibrant colors. Instead, look for anomalies: oddly shaped stones with smooth faces and sharp edges, surfaces that appear greasy rather than vitreous, and a weight in hand that contradicts visual size. Diamonds often present as clear to milky, sometimes with a yellow, green, or brown tint. The luster isn't glassy like quartz. It's subtly oily, with a light diffusion that dulls the brightness. There's a moment most field prospectors encounter early. Panning through creek gravel, a stone catches the light just enough to pause the swirl. But it's not the sparkle that matters. It's how it holds weight, how it reflects light, and what geometric hints its surfaces offer. These three traits, weight, luster, and habit, can reveal more about a potential raw diamond than color or clarity ever could in the wild. Begin with density intuition, what experienced hands call weight in hand. A typical quartz pebble might appear the same size as a diamond-bearing fragment, but it will feel lighter. Quartz runs about 2.65 g/cm3. Diamond is roughly 3.5. That might not sound like much, but over time, handling enough river-worn stones conditions the hand to detect this difference. Especially in fine concentrates, grains 1 to 5, heavier pieces sink faster in the pan and resist swirling displacement. Next comes luster. Diamond has a unique surface reflectivity known as adamantine, a tightly diffused, oily shine that's noticeably different from the glassy, vitreous look of quartz or the dull gleam of feldspar. Under full sun or headlamp, rotate the candidate slowly. You're not looking for a glitter, you're reading how the light wraps the surface. Diamonds reflect brightly even when dirty, with a kind of subdued brilliance that often appears more metallic than mineral. Now consider habit, the stone's natural shape. While diamonds in creek systems are rarely perfect octahedrons, they often preserve hints of their crystalline geometry. Look for angular stones with smooth, curved faces and truncated points. Unlike quartz, which often fractures conchoidally into sharp shards, diamond fragments tend to retain blunt-edged symmetry. Even well-traveled diamonds resist the rounding common in quartz pebbles. Their hardness, 10 on the Mohs scale, makes them wear differently. A candidate that checks all three, feels too heavy for its size, reflects light in a tight non-glassy pattern, and presents geometric regularity, is worth isolating. But it's only the first gate. Many non-diamond materials mimic one or two of these traits. For instance, colorless zircon can be dense and lustered, but rarely maintains diamond's geometric integrity. Similarly, spinel can reflect well, but lacks the distinctive greasy adamantine feel. Keep a loupe handy. At 10x magnification, examine the facet edges and any signs of doubling. True diamonds are singly refractive. Fakes like moissanite often show double images at edges. Also note inclusions. Natural diamonds may show tiny black specks or internal feathers, while glass imitations often have bubbles or swirl lines from manufacturing. This visual triage takes seconds in the field, but it dramatically increases the efficiency of screening. When paired with grid sampling and proper classification by size, the odds of isolating a genuine diamond fragment, no matter how small, improve exponentially. The stone was there all along, just a few inches below the surface, wedged into a riffle behind a submerged cobble. What placed it there wasn't luck. It was the invisible architecture of water flow. Understanding how creeks move, and more importantly, where they slow, is the difference between chasing shadows and recovering diamond-bearing rough. Creeks are dynamic systems, constantly shifting their sediment loads. Yet even in high-flow, predictable physics dictate where heavier particles settle. Diamonds, with their modest but significant density, behave like fine gold, mobile in flood, stable in slack zones. That means they don't scatter evenly, but concentrate in microenvironments shaped by bed geometry and hydrodynamics. The most consistent trap zones occur on inside bends, meanders, where water velocity decreases on the inner curve and accelerates on the outer. This velocity drop forces sediment to fall out of suspension. The heaviest materials, including potential diamonds and their indicator minerals, settle first. These deposits often form in thin lenses beneath layers of lighter silt and organic debris. Even small bends, only a few meters wide, can create these microeddies. Next are obstructions, large rocks, sunken logs, or bedrock shelves. Behind each, water forms a low-pressure shadow where heavies fall out and accumulate. These shadows may only extend a foot or two, but repeated seasonal flows stack deposits over time. Within these zones, diamonds can hide beneath a deceptively normal surface of gravel and sand. Another overlooked trap lies in false bedrock, compacted clay or hardpan layers that behave like impermeable bottoms during flood events. These surfaces prevent further percolation, halting the downward migration of heavier stones. When you encounter a layer where digging becomes suddenly resistant, especially if black sands begin to show, you may have hit a pay lens. Clear that layer slowly, washing and sieving in stages. Mapping these trap zones requires more than instinct. Use flagging tape or GPS pins to mark locations. Note flow direction, gradient, substrate type, and sediment layering. This becomes critical when assessing repeatability. If a diamond is found, you'll want to revisit the same hydraulic signature elsewhere upstream. It's also vital to distinguish active from relic channels. Some modern creeks are too young or disconnected from the original kimberlite source to carry diamonds, but nearby paleo channels, ancient creek beds now dry or buried, may contain concentrated deposits locked in cobble layers beneath soil. Historical aerial maps, LIDAR surveys, and regional geomorphology studies can reveal these ghost flows. A dull red glint in the pan doesn't look like much, until you realize it might have traveled from the Earth's mantle. Pyrope garnet, one of the most reliable indicator minerals for diamond presence, owes its origin to the same deep-source volcanics that carry diamonds to the surface. And when it shows up in creek sediments, it does so for a reason. Pyrope garnets are high-pressure minerals, formed deep within the lithospheric mantle. They ascend via kimberlite or lamproite pipes, vertical conduits of volatile-rich magma that punch through the crust, dragging diamonds and their mineral companions upward. Over time, these pipes weather and erode, releasing their load into the surrounding landscape. If the terrain allows, creeks capture and sort this debris, sending the lighter minerals downstream while concentrating heavies like pyrope in discrete zones. In the field, pyrope appears as a small, rounded to subangular grain, typically 1 form in diameter. The color ranges from pinkish red to deep purple red, but it's not the hue that matters, it's the luster. Pyrope has a distinct glassy to submetallic shine, more vibrant than common almandine garnet. Under sunlight, it can emit a wine-red sparkle, even when embedded in black sand concentrates. Under a hand lens, good pyrope grains show a rich translucency, sometimes with internal zoning. The key to their diagnostic value lies in chemistry. Chrome-rich pyrope, typically with Cr2O3 content above 1%, has strong genetic ties to diamondiferous kimberlites. In professional exploration, Grains are analyzed by microprobe to determine their chrome content. In the field, color and association must suffice. Pyrope appearing alongside ilmenite or chromite in the same heavy concentrate raises the likelihood that these were sourced from a diamond-bearing pipe. Not every heavy, dark grain in your pan leads to diamonds. Some of the most common minerals that settle alongside potential indicators are also the most misleading. Chief among them, magnetite and spinel. One is an iron oxide that responds eagerly to a magnet, the other a complex group of oxides that can easily pass visual inspection, yet often signals nothing beyond local metamorphic terrain. Learning to separate these from true diamond pathfinders is both simple and critical. Magnetite is abundant in many creek systems, especially those draining igneous and metamorphic bedrock. It's opaque, metallic, and dense, around 5.2 g/cm3, and typically settles at the base of the pan. Its defining trait, however, is its magnetic susceptibility. Even a modest neodymium magnet, held beneath the pan or passed over a dry concentrate plate, will pull magnetite grains immediately. They may even clump together. This quick field test eliminates a significant portion of noise in your sample. Any heavy black material that responds strongly can be tagged and set aside, useful for mapping geology, but rarely associated with diamonds. Spinel, on the other hand, is more deceptive. Chromium-rich spinels can occur in kimberlites and lamproites, making them occasional indicator minerals. However, the majority of spinels found in creeks, especially those in high-grade metamorphic terrains, are unrelated to diamond-bearing sources. They're often rounded, dark brown to black, and may show submetallic luster. Their density varies 3.54, 1 g/cm3, which makes them overlap with both garnet and chromite in the pan. Visually, they're difficult to distinguish without a hand lens and side-by-side comparison. Under magnification, spinel grains often appear smoother and more equant than chromite. They lack the pitted or fractured surfaces common in true chrome spinel from deep sources. And unlike ilmenite or magnetite, spinel shows very little reaction to a magnet, useful in eliminating it from the magnetite group, but still ambiguous. To refine your sample, conduct a dry magnet sweep first. Spread the dried pan concentrate on white paper, then pass a neodymium magnet wrapped in a thin plastic bag across the surface. Magnetite and weakly magnetic ilmenite will respond. What remains should be sorted by color, luster, and translucency. Use a 10x loupe to inspect garnet, semi-transparent red, chromite opaque black with granular texture, and suspect spinel smooth, dull black or brownish black. The goal at this stage isn't to confirm diamond presence, but to eliminate known non-indicators and concentrate your efforts. Keep detailed notes: GPS, mesh size, proportion of magnetics versus non-magnetics. A location yielding a mix of weakly magnetic ilmenite, translucent pyrope, and dense chromite is worth pursuing. A sample dominated by magnetite and spinel likely points to non-kimberlitic sources, even if the concentrates appear rich. There's a nuance here. In some terrains, a heavy spinel presence may indicate proximity to ultramafic intrusions, potential but not conclusive environments for diamond transport. That's why pattern mapping matters. A single pan means little in isolation. But if, over a dozen locations, the indicator suite strengthens and the magnetite-spinel ratio drops, the signal becomes harder to ignore. The pan yielded something promising: a small, clear grain, oddly heavy, resistant to swirling, and reflecting light in a soft, oily gleam. But until you test it, it could be quartz, zircon, glass, or one of a dozen other hopefuls. That's where the thermal conductivity tester becomes your most decisive field tool, a pocket-sized device capable of sorting fact from fiction in seconds. Diamonds conduct heat extremely well. This property, more than any visual trait, separates them from nearly every other mineral found in creek systems. Thermal conductivity testers work by applying a tiny pulse of heat through a probe tip and measuring how quickly the stone disperses it. When the reading spikes within a set threshold, the device signals, often with a beep or light, that the specimen has passed the test. Field use models can be found for as little as $15, though professional versions run higher. Choose one with a metal probe tip and a readout scale rather than a simple pass-fail light. The more granular the data, the better your ability to compare borderline cases. Always calibrate before use, and make sure both the probe and the test stone are clean and at ambient temperature. Dirt, oil, or moisture can interfere with results, so carry alcohol wipes and a clean cloth in your kit. Place the suspected diamond on a flat, non-conductive surface. Glass or plastic works. Touch the probe to the flattest surface of the grain. A genuine diamond will spike the meter into the high conductivity zone almost immediately. Quartz, by contrast, will register near zero. Glass won't budge the needle. Moissanite, however, a common synthetic used in jewelry, also conducts well and may pass this test, which is why conductivity alone isn't sufficient for confirmation. Thermal tests become even more valuable when used on a batch of suspects. After screening with sieves and panning, line up 10 to 20 potential grains on a tray. Move quickly through them with the probe, noting which register and which don't. This allows you to triage your sample set and focus attention on the few that truly behave like diamonds. Remember to test across multiple surfaces. A grain might be multifaceted or irregular, and a poor contact angle can yield false negatives. Retest any suspect that nearly passed, especially if it also shows the right luster, habit, and weight. The value of the thermal test is in its speed. Rather than guessing or sending off bulk samples to a lab, you can eliminate 90% of false positives on site. And in high-volume sampling, dozens of pans across a creek grid, that efficiency matters. It's the kind of find that lights up a prospector's hope. A small, brilliant stone, unusually heavy, nearly indestructible under pressure. And it even passes the thermal conductivity test. But in more than half of field cases, it's not diamond. It's zircon or moissanite, two persistent imposters that mimic nearly every key trait except origin. If you don't learn to spot them, you risk chasing the wrong trail and misreading an entire creek system's potential. Zircon is the more common of the two. Found in granitic and metamorphic terrains, it appears as small, often colorless to yellow or brown grains with a vitreous to adamantine luster. It's dense, around 4.6 G/cm3, and will settle with heavies in the pan. Under sunlight or loupe, zircon can sparkle like a cut gem, sometimes with noticeable fire. But its brilliance is a trap. Zircon lacks the unique weight feel of diamond and doesn't exhibit that subtle oily gleam. More critically, it often shows internal zoning, growth bands or cloudy centers visible under 10x magnification. Moissanite, on the other hand, is less common in nature but far more dangerous as a false positive due to synthetic versions flooding the market. Silicon carbide by composition, moissanite registers nearly identical to diamond on most thermal conductivity testers. It's also extremely hard, Mohs 9.25, and nearly as durable. Visually, it's bright and clean, often colorless with slight green or gray overtones. The key to detection lies in optics. Moissanite is doubly refractive. Under a loupe, facet edges may appear doubled, like ghost lines running alongside the true edge. Real diamonds are singly refractive, and this distinction becomes clear under controlled lighting. There's a further trick with moissanite: electrical conductivity. While diamonds are generally non-conductive, most moissanites conduct electricity. A dual-mode tester, thermal and electrical, can instantly separate them. If a stone registers high on thermal and conducts electrically, it's almost certainly moissanite. Zircon, though, requires more care. It doesn't conduct, and it may not fail the thermal test immediately. But zircon often reveals itself during a specific gravity test. While diamond floats just above 3.5 G/cm3, zircon's higher density makes it noticeably heavier by hand, and confirms the difference in a water displacement setup. For in-field practicality, keep a grid system. Any stone that passes thermal gets logged, labeled, and later tested for electrical conductivity and refractive behavior. Stones with cloudy cores, high density, or double refraction should be moved to the hold category, not discarded outright. Some diamonds, especially from certain alluvial deposits, can show odd inclusions or color centers, so patience matters. but your goal is clarity. Eliminate the bulk of misleads while preserving the credible few. A single diamond grain, however convincing, is not a source. It's a clue, one that only gains meaning when echoed across a pattern. That's why repeatability matters. A prospector's real leverage lies not in the find itself, but in the data system behind it. Without methodical gridding and record-keeping, even a genuine discovery can lead nowhere. Begin with site segmentation. Divide your search area into manageable grid units, ideally 5x5 or 10x10 meter squares, depending on terrain complexity. Use GPS coordinates, flagging tape, or color-coded stakes to mark boundaries. Assign each grid a unique identifier, Site A3, Creek Bend 1, etc., and record its metadata, GPS, elevation, substrate type, flow conditions, and visible indicators, e.g., nearby garnet grains, black sands, bedrock exposure. Sample each grid point independently. This prevents data smearing and reveals subtle variations that suggest upstream concentration. Use identical tools and techniques for each grid square. Same sieve mesh sizes, same pan method, same drying and recording procedure. It's not about volume, it's about consistency. Track all results in a field notebook or digital log. For each grid square, record total sample weight, pre-screened material, mesh fractions tested, number and type of suspected indicators, e.g., 3 pyrope garnets, 2 chromite grains. Any thermal density test passes. Notes on magnetic response and luster observations. Also log the absence of indicators. Negative data is vital. It narrows the source window. If Site B4 produces no garnet or heavies while B3 does, that boundary line helps triangulate the upstream source. Over time, this narrows the search zone to a concentrated target. Use mapping software or even graph paper to visualize trends. Are garnet counts increasing upstream? Is ilmenite showing only on one bank? When a second diamond-like grain appears in a new square with matching indicator presence, you've established vector alignment, a directional cue that suggests an eroding source or paleo-channel intersection. Repeatability isn't just scientific rigor, it's financial prudence. Before you invest in deeper excavation, lab testing, or partner interest, you need repeatable data to validate potential. Investors, labs, and geologists trust patterns, not anecdotes. Weather plays a role too. Resample grid sections after high water events or seasonal shifts. New deposition may reveal hidden lenses or expose false bedrock zones previously masked. Always note date and flow conditions. Sediment behavior can change rapidly. One of the most common missteps is oversampling a single, hot square without parallel control sampling. This skews the data and can lead to false conclusions. Your goal is not to chase the richest pan, it's to map the deposit logic. When 3 or more grid squares within a short span produce aligned results, e.g., matching garnet, chromite, and 1 or more conductivity-confirmed grains, you've crossed from anomaly into pattern. And that pattern demands upstream pursuit. Because if you're recovering material here, something farther up has already broken apart. Finding a single diamond in creek gravel can be thrilling, but in isolation it means almost nothing. Without context, it could have traveled for miles, slipped in from glacial action, or even been dumped inadvertently by human activity. The real breakthrough comes not from the find itself, but from decoding its trail. And that trail often begins, or ends, with a breached volcanic pipe. Kimberlite and lamproite pipes are the deep source conduits that originally delivered diamonds to the surface. Over millions of years, erosion liberates those diamonds, scattering them into downstream systems. But erosion is not uniform. Depending on slope, rock hardness, and climate, a pipe might release its load in tight pulses or wide dispersals. That's where proximity logic comes in, learning to read the patterns left behind. Start by analyzing your grid's spatial pattern. If indicator minerals like pyrope, ilmenite, and chromite decrease steadily in one direction and intensify in another, you're tracking a dispersion halo. The denser and more frequent these indicators become, the closer you are to the original erosion point. Diamond counts will usually lag behind the indicator concentration, but follow the same vector. This is where topography becomes vital. Pipes don't erupt randomly. They often exploit weaknesses in the crust, such as fault zones or old structural lineaments. Use topographic maps, geologic overlays, and LIDAR data if available to identify rises, depressions, or breaks in terrain that could reflect a buried or partially eroded pipe. In flatter areas, look for subtle elevation changes, terrace steps, swales, or ancient stream beds now dry or displaced. Consider slope and sediment load. A steep, narrow canyon downstream of an indicator-rich site suggests recent transport. A wide, gravel-filled valley may indicate sediment reworking over centuries. If your high-concentration site lies just below a narrowing in the creek or a bedrock rise, that constriction may have concentrated diamonds released upstream from a degraded source zone. Also factor in lithology. Pipes often intrude into cratonic or ultramafic host rocks, sometimes marked by serpentinite, peridotite, or carbonate alteration zones. If you're seeing greenish, soft-weathering rock fragments, especially if paired with garnet or magnetite, you may be sampling from the pipe's halo without knowing it. Once 2 or more field-verified diamonds appear in grid-aligned sites with strong indicator suites, it's time to consider trenching or upstream augering. These exploratory techniques allow shallow core sampling along presumed dispersion vectors, checking for kimberlitic fragments, blue ground, or elevated indicator counts in situ. Keep your disturbance minimal. Note permissions and land use laws, and record sample depth meticulously. A key red flag is when diamond presence seems too consistent with downstream behavior but drops off sharply upstream. This may indicate a localized breached source, a pipe head, or vent that has weathered to just below the surface. These spots are rare, but they're the true prize. Eroded just enough to release material, but intact enough to study or even mine. At this point, casual prospecting ends. The data now implies a buried structure worth formal investigation. But access, legality, and environmental risk come next, because even if the pipe's footprint is visible on satellite imagery or erosion models, digging into it without permits or geotechnical prep can create hazards and liabilities. You're standing over a bend in the creek where everything aligns: indicator minerals, heavy concentrates, even thermal positive grains that hint at diamond presence. The temptation is strong to dig deeper, maybe open a trench or return with heavier gear. But before you disturb a single inch more, one truth must be confronted. Access without legal rights can end everything. In most jurisdictions, creeks, even those on private land, are subject to layered ownership and use laws. Surface rights do not automatically include mineral rights. In many regions, particularly in the US, Canada, Australia, and parts of Africa, subsurface mineral ownership is held by the state, the crown, or private mineral right holders. If you uncover a diamond without a legal claim or permit, it may not be yours to keep. Worse, unpermitted extraction can trigger fines, seizure of equipment, or criminal charges. Start by verifying land ownership. Use cadastral maps, land registry offices, or regional GIS platforms to determine if the area is public land, private property, or under a mineral claim. Even remote creeks may be part of larger mining leases or exploration licenses, some dormant for years but still valid. Contact the local mining or natural resources agency to inquire about claim status and permitted activities in the region. Next, determine whether the creek itself is classified as navigable or protected. In many countries, waterways are considered public assets, but collection of minerals, even with pans or sieves, may require a prospecting license. In the US, the Bureau of Land Management, BLM, or equivalent state agencies manage access. In Canada, provincial laws govern placer rights. In Australia, exploration permits vary by state, with specific conditions for fossicking, casual hand recovery. Even on land where casual prospecting is allowed, excavation changes the rules. Anything beyond surface collection, digging, trenching, core sampling, typically requires a formal exploration permit. These often include environmental assessments, land use agreements, and in some areas, consultation with indigenous or local communities. Disturbing creeks can trigger erosion, turbidity, and habitat disruption, all of which are closely monitored under waterway protection laws. Insurance and liability must also be considered. If your fieldwork leads to slope failure, contamination, or injury, the legal and financial fallout can be severe. Operating under a valid permit not only protects your rights, it shields you from claims. But legality isn't only about avoiding penalties. It protects your find. If you're operating under a registered claim or permit, any diamonds recovered are officially documented and traceable. This legitimizes your eventual assay submissions, appraisal processes, and sale. Without this chain of custody, even a verified diamond can become unsellable in legitimate markets. So before escalating recovery operations, pause and map your legal perimeter. Who owns the land? Who holds the mineral rights? Is the creek protected? What activity level is permitted here? Answering these questions now sets the foundation for everything that follows. Because once you're operating within the law, every test and every sample counts toward a defensible, documentable discovery. And that makes your next move not just legal, but credible. In the quiet hours after fieldwork, under a tarp or inside a shed, the next layer of sorting begins, not with a pan or probe, but with light. Ultraviolet fluorescence and electrical conductivity offer rapid, non-destructive clues that help prioritize which stones warrant deeper testing. But here's the caution. These are support tests, not confirmations. They help you rule out suspects, not certify winners. Let's begin with UV fluorescence. Many natural diamonds exhibit a bluish glow under long-wave UV light. This fluorescence is caused by trace impurities, typically nitrogen clusters, interacting with UV energy. In the field, a portable UV lamp, 365 nm, can expose this effect in seconds. Place your dried candidate grains on a dark background and shine the beam from several angles. A weak to moderate blue glow, especially a uniform hazy halo, is consistent with diamond. Strong white, green, or yellow fluorescence, on the other hand, is more often seen in synthetic stones, glass, or certain zircons. But not all diamonds fluoresce. Some have no response at all. Others show weak reactions indistinguishable from surrounding minerals. Worse, synthetic moissanite and treated cubic zirconia may show false positives, bright but misleading glows. So while UV can highlight anomalies worth attention, it cannot confirm or eliminate a diamond on its own. Now consider electrical conductivity. Most natural diamonds are poor electrical conductors due to their insulating carbon lattice. Moissanite, however, conducts electricity quite well. This makes dual-mode testers, thermal plus electrical, extremely valuable. A thermal-positive stone that also conducts electricity is almost certainly moissanite. One that conducts heat, but not electricity, remains a strong diamond candidate. To perform the test, use a conductivity meter or a diamond-specific probe with dual functionality. These tools are more expensive than thermal-only testers, but dramatically increase reliability. Test stones in dry, room-temperature conditions, clean and free of surface moisture. These overlapping indicators help you build a risk matrix. The more tests a sample passes, the right weight, right habit, thermal conductivity, correct SG, no electrical conductance, and appropriate fluorescence, the higher its probability of being diamond. This layered approach reduces reliance on any single method and helps you filter out the overwhelming number of fakes, simulants, and natural misleads that creep into even well-sorted concentrates. But resist the temptation to fixate on one perfect stone. What you're building is a dataset. The pattern of indicator minerals, test responses, and site behavior provides a decision framework. It tells you where to concentrate further effort and which samples deserve assay. And once you have a handful of candidates that meet this full diagnostic profile, the next step becomes professional. Not speculative, not hopeful, measurable. Because now you're ready to engage formal verification standards, grid-confirmed material, documented traits, ready for institutional lab validation. No matter how careful your fieldwork, A diamond isn't a diamond until it's verified by an accredited laboratory. Laboratories don't rely on stories. They rely on replicable, instrument-driven diagnostics, and their protocols are clear, conservative, and strict. Understanding what labs test, how they test, and what they expect in a submission can make or break your effort to elevate a promising find into a certified discovery. Start with sample preparation. Before submission, your specimens must be clean, dry, and properly labeled. Stones should be separated by grid zone, size fraction, and type, diamond candidates versus indicator minerals. Each bag or vial should include a sample ID code that links back to your field notebook, date, location, mesh size, weight, and all in-field tests performed. This chain of custody is essential. Labs don't just analyze what you send, they assess how it was handled. For suspected diamonds, labs run a battery of tests. The first is visual confirmation under a gemological microscope, looking for growth features, inclusions, and surface textures typical of natural formation. They check for signs of synthetic processing, laser marks, high-pressure, high-temperature, HPHT halos, or chemical vapor deposition, CVD patterns. Even natural-looking stones can be rejected if growth features aren't internally consistent. Then comes spectroscopy. Infrared and Raman spectroscopy determine the stone's internal carbon structure and trace elements. Type Ia diamonds, those with aggregated nitrogen, make up the bulk of natural diamonds and have distinct spectral patterns. Type Ia stones are rarer, with little to no nitrogen, and often demand further scrutiny to rule out synthetics. Spectroscopy can also detect treatments, irradiation, annealing, or coating that artificially enhance a stone's color. Density and refractive index are measured next. Labs use hydrostatic weighing, more precise than field displacement tests, to confirm specific gravity to 3 decimal places. Optical benches then assess refractive index RI, which for diamond is about 2.42. This value is nearly unique, and stones that deviate even slightly are flagged. Double refraction is also checked to rule out moissanite or spinel. Finally, thermal and electrical conductivity are retested using calibrated instruments. These results are cross-referenced with all other data to build a complete gemological profile. If the stone passes every threshold, the lab issues a certificate, stating origin, natural or synthetic, basic physical properties, and in some cases, inferred geological source. For indicator minerals, labs focus on chemistry. Garnets are tested with electron microprobe or laser ablation to determine Cr2O3, MgO, and Ka-O content, vital for classifying them as G10, diamond compatible, or otherwise. Ilmenite and chromite are also analyzed for chrome and magnesium signatures. A field garnet might look right, but without the right elemental ratios, it won't carry weight as a pathfinder. Be prepared for turnaround times of 2-6 weeks, depending on lab backlog and sample type. Costs vary. Simple thermal confirmation may cost $20-50 per stone. Full spectroscopy and certification can range from $150-300 or more per specimen. Some labs offer bulk rates for indicator mineral chemistry, especially if linked to academic or exploration projects. Accredited labs include institutions like the Gemological Institute of America, GIA, SSEF in Switzerland, and government-affiliated geological survey labs. Always use labs that issue traceable, third-party reports recognized in the gemological or mining sectors. Once verified, a stone becomes more than a find, it becomes evidence. It can be cited in exploration proposals, valued in pre-auction assessments, or licensed in exploration rights negotiations. But perhaps more importantly, it sets a benchmark. Your field results now have a lab-verified counterpart. That first confirmed diamond may be no larger than a grain of rice, yet its value goes beyond carats. In the hands of a disciplined prospector, it becomes a data point, part of a broader geological story that can reveal much more than a single stone. because diamond potential isn't determined by finds alone, but by how those finds pattern in space, in mineralogy, and in structure. That's how small field recoveries scale into large exploration value. It starts with integrating your confirmed samples, diamond and indicator minerals, into a spatial model. Every data point should be mapped against GPS coordinates, local geology, hydrology, and terrain slope. Even in small-scale operations, free tools like QGIS or Google Earth Pro allow layering of this data. Create visual overlays showing indicator mineral concentrations per grid square, thermal density positive finds, sample volume versus yield, terrain features, creek bends, bedrock outcrops, paleochannel traces. This map isn't just for navigation. It's a predictive tool. If multiple garnet-rich zones align upstream of a confirmed diamond site, that axis likely shadows a buried erosion source. If chromite and ilmenite appear strongly on only one side of a creek, lateral migration or channel drift may be hiding the main deposit. These inferences turn sporadic hits into testable hypotheses. Next, look for vertical consistency. If your sampling spans different elevation zones, modern creeks, floodplains, and old terrace levels, you can infer erosion timelines. Diamonds found only at higher elevations may be part of an ancient deposit now cut off from active flow. If lower creek zones show more indicator diversity, they may be acting as collectors from multiple upstream sources. Data density matters. The more grid points with indicator counts and mineralogy, the stronger your model. Even grids that produce no diamonds contribute by defining the boundary of the system. These null zones help tighten the perimeter of exploration and eliminate wasted effort. Some prospectors stop at mapping, but big data also opens doors. Academic institutions, junior mining companies, and geological surveys often look for early-stage leads with spatial rigor. A well-documented cluster of pyrope-rich grids and one or two confirmed microdiamonds can form the basis of an exploration partnership. You may license your data, sell access, or gain inclusion in broader survey efforts. There's also value in sample consistency over time. Resampling after floods, fire events, or seismic activity can show shifts in concentration. If a site consistently produces diamond-positive concentrate across years, its credibility as a commercial target rises dramatically. This approach, repetition, logging, and modeling, is what separates a casual prospector from a credible early-stage explorer. It also protects you from false highs. A single recovered diamond without pattern support is exciting, but financially unstable. A site with no diamonds, but rich in high-chrome pyrope and G10 garnet across multiple zones, may be even more valuable in the long run. Each of these regions shares several traits: ancient cratonic crust, known primary pipes, even if not fully mined, and preserved paleochannels where erosion products accumulated. But for every working terrain, there are dozens of false parallels. Take, for example, the Appalachian region in the eastern U.S. Despite abundant garnet, magnetite, and black sands, it lacks kimberlitic source rocks. Prospectors often mistake metamorphic garnet and heavy mineral concentrates for indicator sweets, spending years chasing a deposit that doesn't exist. The same occurs in Central Europe, parts of Southeast Asia, and across volcanic arcs where high-grade metamorphic rocks yield heavy minerals but no diamonds. Even within a favorable region, micro-variations can change everything. A creek draining the backside of a kimberlite may yield nothing, while a tributary on the forward erosion slope carries diamonds in multiple terraces. That's why topographic inversion, where erosion-resistant pipes form upland plateaus rather than depressions, must be considered. Mapping paleochannels is critical. Many diamond-rich creeks today are not active transport zones but vestiges of ancient flow patterns. In such cases, current water doesn't matter. What matters is where water flowed during the key erosion window. This is why LIDAR and historical geomorphic modeling have become powerful tools in modern prospecting. In practical terms, your method, sieving, panning, testing, only works when upstream geology includes eroded diamond pipes and when sediment hasn't been completely diluted by reworking or masked by overburden. If indicator minerals appear in quantity but without follow-up diamond hits, reassess. Are they metamorphic in origin? Is the creek post-glacial with distant sediment inputs? A raw diamond pulled from creek gravel holds immediate promise, but its final worth depends on what it can become. The market for rough diamonds is both technical and psychological, balancing physical attributes against provenance and potential. Before a stone ever sees the inside of a cutter's wheel or an auction catalog, it must answer a series of unforgiving questions. Can it be cut? Will it hold clarity? And does its origin elevate or diminish its value? Let's start with the fundamentals. Rough diamonds are evaluated on the 4 Cs, carat, color, clarity, and cut, but in raw form, only the first 3 can be directly assessed. Carat weight is straightforward. A 1-carat rough stone equals 0.2 grams, but size alone doesn't dictate price. A heavily included 1-carat stone may be worth less than a clean 0.5-carat one, depending on clarity and potential yield. Clarity assessment in the rough is specialized. Stones are examined under magnification and bright light for internal fractures, feathers, mineral inclusions, and surface blemishes. Certain inclusions, like black carbon spots or tension cracks, can prevent clean cuts or cause the stone to shatter during processing. Others may be shallow enough to be polished away. Natural etching, common in alluvial stones, can sometimes mimic damage but may not affect cutting yield. Color is another determinant. While high-end white diamonds, DF range, command premium prices, subtle tints, especially yellow, brown, or green, can drastically affect value. Paradoxically, strong natural colors like pink, blue, or deep champagne may drive prices upward if natural and vivid. Stones from known origins like argile or the Congo with rare hues often exceed standard per carat expectations. But rough stones rarely sell by carat alone. They are valued by estimated yield, the percentage of the rough's weight that can be retained in a cut gem. A well-formed octahedral rough with minimal inclusions may yield 40–50% as finished stone. A flattened or flawed crystal may yield only 20–25%. Dealers and cutters price accordingly, using 10x loops, modeling software, and years of intuition to estimate the potential. Now consider provenance. A diamond with traceable origin from a known kimberlite, certified alluvial field, or legal artisanal site carries more than physical value. It carries credibility. Conflict-free sourcing, environmental compliance, and verified chain of custody all increase salability, especially in regulated markets like the EU, US, and Japan. A rough diamond of modest clarity but confirmed ethical origin may outperform a higher-grade stone with murky history. Field-found stones, especially from informal sectors or unregistered territories, often struggle in this regard. Without documentation, grid logs, sampling maps, lab certification, they enter a gray market of speculative valuation. Some buyers offer only a fraction of potential value, citing resale risks. Others may refuse altogether, wary of legal entanglements or fraud. To bridge this gap, verified lab results paired with documented sample history elevate a stone's profile. A thermal positive, density-confirmed, lab-certified natural diamond with GPS-linked grid data and mineralogical context becomes more than a find. It becomes a product. Such stones can be submitted to auction houses, boutique gem dealers, or partnerships with cutting firms who value full traceability. Pricing varies wildly. A clean, rough white diamond under 0.5 carats may bring $100–300 per carat wholesale. Stones over 1 carat, with high clarity, climb steeply, into the $1,000–5,000 range and beyond, depending on yield and market trends. Rare colors or provenance-backed specimens can fetch multiples of standard rates. But with value comes risk. The next danger isn't in the field but in the transaction. lowball offers, swapped stones, or outright fraud. And without proper protections, the stone you found can become someone else's payday. That's why the next step is understanding how diamonds get lowballed, switched, or lost, and what you can do to prevent it. Because after all this effort, the final mistake would be letting it go for a fraction of its worth. You've done the work, field-tested, lab-verified, documented every step. But the moment a rough diamond enters the market, another set of forces takes over. The trade in uncut stones is notorious for one thing above all: opacity. And without strict controls, even a legitimate discovery can be lowballed, swapped, or legally separated from its finder. Understanding how fraud enters the chain and how to prevent it is not just protection, it's preservation of value. The first vulnerability is knowledge imbalance. Many field prospectors, even experienced ones, are not cutting experts or traders. Buyers know this. They leverage uncertainty. This stone has a feather. It won't yield more than 20%, or it's probably not natural, to erode confidence and drop the offer price. In some cases, they'll imply the need for lab confirmation while quietly pocketing a sample already confirmed. A clean 0.9 carat rough might be offered $200, then quietly resold for 5 times that after minimal cutting. To counter this, never present a stone without supporting documentation. Lab reports, SG data, thermal readings, and high magnification photos lock down its identity. Record weight to the hundredth of a gram and photograph it from all angles. Better yet, measure key dimensions, length, width, height, to within 0.1. Even tiny discrepancies can reveal swaps. Keep this record set before showing it to any buyer. The second danger is substitution fraud, an old dealer's trick. You show your verified stone. The buyer handles it, turns around, accidentally drops it, or sets it beside another of similar size. Moments later, you're handed back a lookalike, same size, same weight, but worthless. This is why all evaluations should be done under your supervision, on a well-lit surface, with zero unsupervised handling. Use a gemstone tray or lidded box with a foam insert. Never allow a stone to leave your line of sight until payment clears. Third, chain of custody confusion. In some regions, especially where artisanal mining overlaps with formal markets, the chain of ownership can become legally murky. If a stone is discovered on unclaimed but government-managed land, some agencies may assert ownership or levy retrospective royalties, even if you've performed all fieldwork legally. Clarify your jurisdiction's rules about self-discovery, artisanal claims, and revenue sharing. Documentation doesn't stop with proof of find, it continues into transfer. Any sale or consignment should include a written agreement, stone ID, weight, buyer's information, sale terms, and conditional clauses. If selling rough to cutter, include provisions for post-cut share or return rights if the stone fails yield expectations. Use dated photos of the handoff, preferably with a witness present. Today's phone cameras with geotagging and timestamping are admissible in many legal contexts. Don't overlook digital scams either. Offers via social media or unverified platforms often bait finders with inflated valuations, then request shipments for evaluation, after which the stone is never returned. The rule here is simple: no stone moves without secured payment or verifiable escrow. Even among reputable dealers, pressure tactics can distort value. Phrases like "the market's soft right now" or "you won't get better than this" are designed to create urgency. Counter this with evidence, recent auction comparables, lab cert comparisons, or documented recovery history. The more verifiable your story, the less leverage the buyer holds. Lastly, remember that true value extends beyond the stone. If your find is linked to a promising site, especially with documented indicator minerals and grid data, you may hold more value in the source than the stone itself. Consider licensing, joint ventures, or data sales as an alternative to a one-off trade. The tray held 3 stones, each isolated in a foam-lined slot. All were pulled from the same creek system, less than 50 meters apart. To the naked eye, they looked similar, rough, translucent, and irregularly shaped. Each had passed basic thermal conductivity in the field, but now, under controlled conditions, only one would prove to be diamond. The others, though convincing, were deliberate countertests. This is the moment where field confidence is tested against the full suite of mineralogical truth. Candidate A was the largest, 1 carats with a subtle yellow tint and smooth faces. Under a 10x loop, it showed what appeared to be growth lines and 2 internal specks. It passed thermal and did not conduct electricity. In water displacement, its SG measured 4.65, too heavy for diamond. The lab's infrared spectroscopy confirmed it: zircon. High natural density, high luster, and even weak fluorescence under UV. But the refractive index and spectrum were conclusive: not a diamond. Candidate B was smaller, 0.72 carats, glassy, colorless, and slightly more rounded. It passed thermal again. Electrical conductivity, however, was clearly present. Under magnification, slight facet doubling appeared at one edge, a sign of double refraction. Specific gravity read 3.2. The lab result: synthetic moissanite. A near-perfect field imposter, especially for stones under 1 carat. Without dual-mode testing, it would have passed every in-field check. Candidate C was the least dramatic visually, 0.56 carats, off-white, slightly greasy luster with a subtle asymmetry to its geometry. In hand, it felt heavier than its size suggested. It passed thermal conductivity and failed electrical. SG measured 3.51. Under UV, it emitted a faint blue haze, barely perceptible. The lab confirmed it as a natural diamond, type Ia with minor inclusions. Its origin, inferred from mineral inclusions and spectral trace, was alluvial, consistent with eroded kimberlite transport. This side-by-side comparison revealed 2 critical lessons. First, no single field test is definitive. Even sophisticated tools can be tricked by mimics. Only a full diagnostic suite, thermal, electrical, SG, optical, and spectral, can decisively separate real from fake. Second, appearance is unreliable. Candidate C, the least impressive to look at, held the most value. This scenario also proved the importance of process. All 3 stones were tracked from initial recovery to lab analysis through documented grid samples, video logs, and test records. Without this chain, the verified diamond would carry less market weight, and the learning opportunity from the false positives would be lost. For field prospectors, this is the pivot point. Once a verified stone stands beside its imitators, the work shifts from identification to strategy. Do you sell the stone, cut it, license the find, or leverage the discovery to explore deeper?